After talking about finite difference methods, let's now discuss finite element methods. And they are rather different in approach because rather than solving a differential equation directly, they take some sort of oblique way of arriving at the answer of the problem. But we'll see that later on. Let's briefly discuss a basic recipe that most of finite elements follow so that you can get an idea for what's going on in these methods. The first step in the recipe of cooking with finite elements is, if you have a certain structure that you want to model, is you subdivide that structure into a number of subregions, which are finite in space. And this is why we call the method the finite element method. So because these subregions, they're the elements. Now you see the shape of these elements that can be quite irregular. They do not need to be all the same, which is very different from the typical regular meshes that are used in finite difference methods. And that has a big advantage if you want to model, for example, a curved structure like this, because if you were to do the same thing using the regular grids of a finite difference method like this, then you see if you were to approach this curved boundary, you typically would get a sort of like staircase profile that approximates this curved boundary, which is a very poor approximation. You can see with these triangular meshes where the edges can be oriented along any angle that you get a much better approximation of this curved boundary. So that's an advantage of finite element methods. The second advantage is that, as I mentioned, this grid can be irregular. Not all elements need to be the same size. So you can say, for example, if you suspect that the field varies a lot in this corner region, that there you can locally refine the mesh and take smaller triangles. So this is like a locally refined mesh giving you a much better resolution where you need it. It's much more efficient. You can do something similar in finite difference methods, but there it turns out to be typically much more involved because you need to worry about parasitic reflections that can occur if you go from the coarse grid to the fine grid. Whereas in finite element methods, it's much more straightforward to have elements of different sizes. Okay, so that's step one, subdividing the structure into our finite elements. In step two, we're going to figure out how we're going to represent the unknown, which in our case will be the field typically, in each of these elements. So let's say we're looking at a certain element L, and we're going to look at the field in that element. How are we going to represent this? Well, we're going to represent this by having some sort of approximation as a sum of a limited number of basis functions. So we have an index I, running from 1 to m, where m is the number of basis functions that we're going to use to approximate our function. So let's look at the 2D case where the basis functions are a function of x and y. So in each element we have I of these basis functions. So we have rather m of these basis functions with an index I running from 1 to m. And we should also allow for the fact that these basis functions can be different from element to element. So we have another index L here. And then, of course, we have expansion coefficients for these basis functions, which are the unknowns of our problem. So ui, and also they are different for each element L. So these guys, they are known. We choose them in advance based on the requirements of our problem and the required resolution. And these guys, the u's, they are the unknown coefficients. And figuring out what they should be, that's basically the whole point of the game here. Okay, so this is the representation we're going to use for our unknown fields in each of the elements. An expansion in a finite number of known basis functions. Let's go to step number 3. So far, we've looked at each element individually. Obviously, these elements, they are interdependent, right? One element is next to another element. So there are some constraints that you can exploit when you are gluing these different elements together. Typically, what you have is that the field is continuous if you move across the boundaries of the different elements. And that is something you can exploit to basically reduce the number of unknowns. So rather than having m, the number of basis functions, times L, the number of elements, you end up with a smaller number because many of those will be counted twice, one for one element and one for the adjacent element. So in step 3, we've glued together all our elements. And now in step 4, we're going to start seeing the magic of the finite element methods, because what we're doing there is not tackling the differential equation directly. Rather, we do something mysterious. We're going to define a certain quantity J, which is calculated based on the field. And obviously the field, the only thing that matters there for our purposes is that this is then a function of our unknown expansion coefficients. So we're going to write down a mysterious quantity like this, calculated from the field, which often, but not always, is the total energy of the system. And this is what we're going to be working with in step 5, which is the final step, which is to say, well, we're going to figure out what our unknown coefficients U are, not by solving the differential equation directly, but rather by minimizing this quantity J. So the idea is to find our unknown coefficients, UIL, such that we end up with a minimum of J, a minimum of the energy, which is a physical thing to do if J corresponds to your total energy. How do you do this in practice? Well, you do basically the obvious thing, which is what's also called the Rayleigh-Ritz method. So Rayleigh-Ritz method. So what these guys did is just simply take the partial derivative of the quantity you want to minimize with respect to your unknown coefficients. And then you put them equal to 0. You repeat that for all the unknowns, and then you basically end up with as many equations as you have unknowns. And then hopefully these are linear equations, and then you can solve them using your favorite linear algebra package. So in a nutshell, this is the recipe for finite element methods. What we will be doing in the next set of videos is making this more concrete for the case of the one-dimensional Helmholtz equation.